Okay, so we put this on pause. Remember, this was the logistic differential equation. The reason we put it on pause is because it's obviously a separable differential equation. It's a little bit of work, so that's all this section is about. Let's separate it and let's actually find the solution to the logistic differential equation, the actual population growth. And again, it's paused now because we needed separable in order to discuss it. So we're going to put the t and the k over here on the right, and then on the left-hand side, we move all the stuff with p. Okay. Now, this is just algebra, and the one on the right is easier to deal with. That's why we're doing it. So you're multiplying top and bottom by capital K here. So that's why it's 1 minus just p, and it cancels here on the bottom, and you get the k on top. And like I said, it's just easier. And remember, these are both constants. This is a constant, and this k is also a constant. They're different, but they're both constants. Notice that, how do we deal with this? Well, if I write it instead of p with, like, let's say x, right? K is a constant, so it doesn't matter. So if I had something like, let's say 1 over x times 1 minus x, right? How would I integrate that? Because eventually that's what we're going to have to do. And hopefully you recall this is rational functions. You need partial fraction decomposition. So that's where this comes from. So I split it into we don't have x, we have p. So it's p and k minus p. And so there's some work in here. Again, I just broke it up and did the a over p plus b over k minus p. And you go ahead and solve. And so we split it up into that. So this is what we're left with. 1 over p plus the 1 over k minus p and the 1k. Okay, so now we're ready to integrate. So there's an ln, and a kt plus c. Now notice, because I have, well, first of all, where'd the minus come from, right? So if this is, in this particular one here, if u is k minus p, remember du then is minus 1 times dp. So you need to fix that with a minus in and out. That's where that comes from. And then this is your log rules, right? So the ln of a minus the ln of b is the ln of a over b. Okay, so I've just rearranged that in that sense here. Now notice that, well, where'd that minus come from? I multiplied both sides by -1, so this will become a minus and a plus, and this will be a minus. Why is it not minus c? Because it's a c. Doesn't matter. You can. It doesn't really make a difference. And so that's why the k minus p is on top of this fraction. Okay? So then, of course, it's e, right, to both sides. So that takes care of the... and then again, why did I combine it? Just because I want to show off my log properties? No. If you did e at this stage, you'd kind of be stuck, right? So that's why you have to put it together. So I get, again, e to the c is just a, so I get this situation here. And then again, some more algebra will yield this. So I multiply both sides by p, and then add the p over to the right, factor it out, and move that over. This is our solution. Okay, so that's the solution to the logistical differential equation. P of t is carrying capacity over 1 plus a e to the minus kt. All right, so it does have an exponential in it, obviously, but it's not just a e to the kt. Okay, there's a little bit more involved. Again, if you let a is the initial amount, right, when at time 0, if you let t be 0, you can simplify a. So p0 is just the initial population. So a is always going to be your carrying capacity minus your initial population over your initial population. Again, that's just letting t be 0 here. Okay, which is exactly what this says here. So let's do one of these. We'll see how this works, right? So we stock a lake with 400 fish, and we know the lake has a carrying capacity of 10,000. And after the first year, we have triple the amount of fish, so let's find an expression for the size and population. Okay, so initial population, P0 is 400, and we also know that after a year it triples, so P of 1 is 1,200. And we also can figure out A, right? It's carrying capacity minus initial population, so it's 10,000 minus 400 over 400, which gives us 24. So putting in A in, I get this situation here. But again, I still need to solve K, or solve for K. Again, I have a point in order to do that, right? When P is 1,200, a T is 1, so that enables me to solve for K, and then of course that would go back in. Okay. And then once you have that expression, you can then determine how many fish after how many years, or how long it would take to get to a certain number of fish. So this one's kind of interesting. I want to discuss just for a second. This is the second derivative. So what you want to do is you want to start with the logistic equation, which is dp dt is equal to k times p times 1 minus k over p over k, right? That's your standard differential. Now notice that p is the variable here. So this is a capital K, and this is a lower k. So what I want you to do is to find the second derivative of this. You're going to need to differentiate this. And remember, p is your variable, so you will need product rule and chain. Okay. So you're going to get the derivative of pk times this plus this times the derivative of k times p. And remember, this is also, it's implicit, right? You're differentiating with respect to t. So every time you differentiate p, it's times dp dt. So you're going to do the product rule, try this out, and then you'll do the chain rule, and then you'll get, and I'm going to post a key for this as well, so you'll be able to follow along. You'll get some dp dt's, and then you'll replace dp dt's with this, because that's what dp dt is. And you do all this algebra, and you should get this. So why am I making you go through all that? Well, it's a good exercise and review, of course, but you need it to answer question 2. So you'll think about that. And then this is more of a straightforward type of question here. Okay. So there you have it.